Hello, and welcome to a conversation about Newton's laws. Newton was a physicist and mathematician who apparently lived from 1642 to 1726. He was also involved in our conversation on gravity. He was the guy who came up with the universal theory of gravity, invented calculus, arguably, and came up with the laws we're going to talk about today. He had three laws. The first law was an object at rest stays at rest, and an object in motion stays in motion unless acted on by an unbalanced force. There's a couple of different ways this was worded. It was originally written in Latin, so it's been translated a couple of times, but this is the way I like it written best. His second law is a mathematical law. It was also written in Latin, but it's much easier to understand as sigma F is equal to ma. Let's talk about this little sigma. This means to add, oh, this is written a little bit funny, to add all them up. So this means add up all of the forces, and that's going to be equal to the mass of an object times that object's acceleration. So if there's more than one force, you have to add them all up, but if there's only one force, then adding them all up is easy. It's just what that force is. I'm going to talk about all three of them, and then I'm going to go through them in much more detail. So if that doesn't make sense yet, don't panic too much. And Newton's third law is, for every action, there is an equal and opposite reaction. This force explicitly talks about forces. And some people like to think of it as like for some forces there's an equal and opposite reaction, or for some forces it's kind of close-ish. But this law is pretty explicit. It's every single force that happens in the whole universe, there is an equal and opposite force. When he published these laws, he made it cause a bit of unrest in the academic society. This wasn't the prevailing opinion at the time. And when we think about things in terms of our Earth view, it's not typically how we view things, especially Newton's first law: an object at rest stays at rest, and an object in motion stays in motion unless acted on by an unbalanced force. The prevailing opinion of the time was that everything naturally came to rest unless you did something to it. And when we look at just about every single thing on Earth, that's true. If you give something a roll, or you give something a slide, or you give something a push, you have to make it move, and then it eventually comes to a stop again. It's when we look at there's a weird pop-up that I don't know if you can see. I'm going to see if we can get rid of it. Um, uh, Super distracting. There we go. It was from Newton. Um, it's when we start looking at the solar system and the galaxy and the universe that we start seeing all of these objects that are perpetually in motion and never stop unless they're acted on by an outside force. And then that made him think about these objects on Earth, and then he realizes that in most scenarios, what makes things come to a stop isn't that that's their natural and desired state, but that a force of friction acts on them, and that would be the unbalanced force. If you keep pushing on it, then you can accelerate it with that unbalanced force as well. So let's look at a couple of examples that we can use Newton's first law explicitly to talk about. And the first one is seatbelts. So we use seatbelts at cars. They're mandatory in all cars now in Canada. Not only mandatory that they're in cars, but mandatory that people wear them. And so what Newton's law says, and we can use this to talk about why seatbelts are important. And I think I have down here a YouTube video. Let's see if we can give it a poke and open it up. That's going to talk about seatbelts for us for a second. For some reason, it opens up two. We'll close one of them. Basically, the reason we have seatbelts is that if we are sitting in a car and the car is moving at 100 kilometers an hour, we are an object in motion. The car is also an object in motion. If that car suddenly comes to a stop and we are not wearing a seatbelt, we will continue in motion until an outside force or an unbalanced force helps us come to rest. And what a seatbelt does is it gives us some
Have
type
fun
of,
and learn
oh
math at the
no,
same
more
time
ads.
with Adapted Mind, a fun learning game for ages
We're
5.
going to skip these ads. And then we should come up with a bit
We
of a crash test.
recently conducted a test to show what can happen when there's a crash and the person in the back is unbuckled. In a simulated 35-mile-per-hour impact, the unbelted dummy slams into the back of the driver's seat, pushing the driver dummy into the deploying airbag and steering wheel. Drivers are twice as likely to be killed in crashes when the occupant behind them is unrestrained.
I thought that was interesting because we usually think about the driver getting injured in a car accident, but in that case, it's the person in the back seat who isn't wearing a seat belt, and then it's the seat in front of them that provides the unbalanced force to stop them, and so there's even more force on that driver. Of course, when we think about the driver not wearing a seatbelt, the unbalanced force that will eventually stop them if that car comes to a rest, either hitting a tree or another car or a brick wall, it'll either be the the steering column, which attaches your steering wheel to your car, or whatever is outside the car. There's examples of people in car accidents being flung out through the front windshield. Seatbelts. Wear your seatbelt. Step two, I think example two is a little bit more lighthearted than seatbelts in car accidents. It's ketchup bottles. You got to think of your old school glass ketchup bottles and how did you get your ketchup out? And there was a bunch of different ways you could do it to get your ketchup out, but that last little inch at the bottom was super hard. And one of the tricks people used, and still do if you've got a glass ketchup bottle, is to get that ketchup bottle moving down as fast as you can with a swing of your arm and then stop at the very bottom of your swing so that ideally the ketchup glass bottle stops, but the ketchup keeps going. So object in motion stays in motion. That ketchup will stay in motion unless acted on by an outside force. I think our next two have to do with coffee. Oh, airplane coffee is one of my favorite examples. You can imagine yourself sitting in your airplane. Well, probably not right now. Nobody's sitting in airplanes anymore. But maybe one day again soon, people will be sitting in airplanes, drinking your cup of coffee. You are a good airplane passenger, so you have your seatbelt on at all times. You are leaning over your cup of coffee to take a sip and holding on to your cup of coffee, and the plane hits turbulence, and the plane immediately drops down exactly 1 meter. You're attached to the airplane with your seatbelt because we just talked about seatbelts. So you also go down 1 meter. But what happens to the coffee in the coffee cup? What most people will say is the coffee splashed you in the face. But that's not exactly true, and it's explicitly not true with Newton's first law as used as an explanation. What happens is the coffee stays exactly where it is, and your face very rudely splashes straight down through the coffee. So the coffee stays where it is, and the person's face gets squished straight down through the coffee, which stays where it is in one spot. I think our last one to talk about is also coffee, car roof coffee. I think if we haven't seen this on the movies or experienced it in real life, we can imagine it pretty easily. You take your hot coffee, you stick it on top of your car, and then you load your car up, and then you get in your car and drive away, and your coffee stays on top of the car. If it's not a coffee, it's something else. I think this happens pretty regularly to people. It gets left on the top of a car. You can imagine if that roof is really icy, people will say, well, the coffee falls off the back of the car. And that's not really what happens. The coffee stays exactly where it is, and the car drives out from underneath the coffee. It usually doesn't happen actually right away. What usually happens is the coffee's on top of the car, and if we draw a box van and put the coffee on top of the car, what usually happens is when it goes around a corner. So the car actually drives out from underneath the coffee, so there's actually a force happening on the car to make it turn. And since that force is not on the coffee, it keeps going in a straight line. And so it ends up sliding, or the car ends up turning out from underneath the coffee. This one is super interesting to watch, and I usually watch it about 4 or 5 times to kind of get the idea going in class. But we're going to watch it once, and it's a movie by the Slow Mo guys. And let's see if I can get it to open first try without any hassle. Things are looking good. I suspect, though, that we might have to deal with an ad. I'm not sure how much preamble they'll give you, but essentially what they've done is they've taken a soccer ball and they've filled it up with water, and then they throw it at someone and film it in slow motion. I'm going to make this one full screen so we get the full. Well, apparently I'm not. And what we want to do is we want to actually see the slow motion part. And watch as he starts to cringe a little bit as that ball comes in, because he knows it's not going to be pleasant. And as we watch it, I think we get it once more in slower motion.
Is that any good or not? Yeah, it's pretty good.
No, I think that's it. You can see that as the ball hits his face, his skull is solid, so that moves first. And this is weird to think about, but your skin and eyeballs are not firmly attached to your face. So only when the connective tissue goes tight do those start to move. So if you watch his eyeballs on this next round, they stay where they are as his skull moves. Craziness.
Is that any good or not?
I highly recommend giving that one a watch on your own time, maybe once or twice. There's a little plug for the slow-mo guys. Let's talk about Newton's third law. We're going to talk about Newton's third law first, and then we're going to go back and talk about the second law. So Newton's third law unpacked. The first thing we want to talk about is jumping. So for every action, there is an equal and opposite reaction. So we want to use that law to describe how you actually jump. What most people will say is, well, you push with your legs and then you go up. But if you think about that, logically, that sentence doesn't actually make sense. Your legs are pushing down, but you go up. You're not even pushing in the same direction that you're going. So what's actually happening in terms of Newton's third law is you push on the ground with a certain force, and the ground pushes back with an equal and opposite force. So it's actually the ground that rockets you up into the air, not your legs. You can imagine if you tried to jump in space, if the ground wasn't there, you would just be flailing your legs miserably. It wouldn't work at all. It's the ground that rockets you up into space. Similarly with walking. You're taking steps forward, what most people will say is it's your legs that propel you forward. But it's not actually your legs that make you go forward. What's actually making you go forward is you gently push back with your legs, and it's a force of friction that pushes you forward. You can imagine just trying to run on an ice rink. If you start from rest and then you start to run as fast as you can, your legs will slip. If there's no force of friction, you can't go forward. So it's the force of friction that makes you go forward. Similarly with airplanes, the airplane wings push down on the air and the air pushes up on the wings. And spaceships are super cool because they could not move without Newton's third law. There is nothing to push against in space. So what spaceships have to do is they take something with them to push against. And what they take is that rocket fuel. And the only reason to light the rocket fuel on fire is to make it move faster. There's no real reason. On Earth, it kind of like pushes against things, but in space, you just want to push on it as hard as you can. This would work not as well, but with an equal principle. If you just took a chair up and you're sitting in space, you've got a chair in your hands, and if you throw the chair away from you, so throwing, you're applying a force to that chair, and you will experience an equal and opposite force going backwards. And that's what the spaceship does. It takes fuel with it, and it throws fuel out the bottom of the spaceship with a force, the acts of force on the fuel, and then the fuel in turn is what pushes the spaceship. As I said previously, this was all kind of new and kind of odd. And when it was published, people were like, well, no, that's not how the world works. And I can't remember who came up with it, but someone came up with what's called the horse's paradox. And it's going to sound a little bit funny. It's a little bit folksy, a little bit of a tale. And so the story goes that, and this was a counterexample. This is an example that someone came up with that went, horses wouldn't work if Newton was right. And the story goes that a farmer is going to take his horses to market, and the horse knows just enough Newton's laws that he argues. He says, no, and no matter how hard I pull on the cart will pull back on me, and I won't be able to go anywhere. Because if every force had an equal and opposite reaction, that would be true. And this was the story that people came up with to try and disprove Newton's laws. He said if Newton's law was right, horses and carriages wouldn't work. We know that horses and carriages do work, therefore Newton must be wrong. But again, they were thinking about it not quite the complete picture. It's true that the force would pull on the cart with a force, and the cart would pull back on the horse with an equal and opposite force, but neither of those two forces are the forces that make either of them move. The force that makes the horse move is on the ground. So the force pushes back on the ground, and the ground pushes forward on the horse. So the horse moves not against the cart, but against the ground. And those two forces, those forces I've drawn in green, would also be equal and opposite. So on the horse, there would be an unequal pair of forces. The green force would be larger than the red force, therefore the horse would move forwards, and would also take the cart along with it. It took people a little while to wrap their minds around this, probably measured in years. We're going to hope that you guys can wrap your mind around it substantially faster. We're going to look at a couple of examples to do with Newton's second law. An asteroid accelerates from 7 meters per second to 29 meters per second over 300 seconds. If the net force causing this acceleration, I'm down too far. I want to do example 1 first, not example 2. Hercules applies a 7,000 Newton force to a 1,000 kilogram boulder. What is the acceleration of the boulder? I meant to write a 700 Newton net force to a 1,000 kilogram boulder. What is the acceleration of the boulder? This one is pretty straightforward because we know the net force, which is this symbol here, sigma and F together, is the net force. And it's 7,000 newtons in this particular example. The mass of the object that's being accelerated is 1,000 kilograms, and we're asked for an acceleration. So, looking at our formula, sigma F is equal to ma. I can manipulate it just like I would. The sigma and the F always live together. It's sort of like a subscript or a superscript. They stay together. It's one variable. I can divide both sides by m to solve for a, and I get my acceleration is equal to sigma F over m, or my net force. Some people will write this as F net, but as we've seen, we use the subscript to tell us what type of force it is. So when I read F net, what I think about is like the force from a soccer net or basketball net or a hockey net or something, and it confuses me. And this sigma symbol is much more universally accepted as like a sum of, if you haven't seen it yet in math, most of you will. So sigma F is equal to 7,000, which is our net force is 7,000. I don't usually put units in. I don't know why I did now. Divided by 1,000. So my acceleration, 7 meters per second squared. There we go. Let's look at example 2. These are going to get a little bit more complex. Example 2, an asteroid accelerates from 7 meters per second to 29 meters per second over 300 seconds. If the net force causing the acceleration is 7.05 times 10 to the 4 newtons, what is the mass of the asteroid? As a side note, this is actually how you can figure out masses of extrasolar objects, is you can look at what the net force would be on them and then look at how fast they're accelerating, because you can measure both of those things, and from that you can determine the mass of extrasolar objects. It's pretty cool. You could discover masses of suns and planets and asteroids. So we'll notice that we've been talking about Newton's second law, sigma F is equal to ma, or my net force is equal to mass times acceleration. I am given a net force, which is nice, 7.05 times 10 to the 4. I'm crowding a little bit, and I can conveniently move things. So let's move them. Let's move that over there. I am given, and I'm looking for things. I'm not given a mass, and I'm not given an acceleration, so I'm a little bit stuck. So what we're going to have to do is realize that my acceleration lives in two worlds. It lives in both the kinematics world and now the dynamics world, which means I might have to use kinematics to find my acceleration. So I'm now looking for kinematics details, and I realized I've got an initial velocity, which is 7 meters per second. I've got a final velocity, which is 29 meters per second. And I've got a time, which is 300 seconds. And I realize that, of course, I can find my acceleration using kinematics. What am I going to use? I should be able to use Vf is equal to V naught plus AT. I know Vf, I know V naught, I know T, I'm looking for A, so I know everything in the equation except for one unknown. I could rearrange it, and I get A is equal to Vf minus V naught over T, so that my acceleration is going to be equal to 29 minus 7 divided by 300, and I find that my acceleration will then be equal to a 0.73333 meters per second squared. I kept all those decimals because I'm not at a final answer yet, and I don't want to end up with rounding error before I'm done. So I like to keep at least 5 decimals. Ideally, you just kind of leave it in your calculator. If you want to write down less because it's a pain, you could kind of go like this, and that tells me with the ellipses afterwards that you're carrying all those decimals in your calculator and just don't want to write them down, and that's completely fine too. So now that I know my acceleration, I can rearrange Newton's second law, F is equal to ma, into m is equal to a over sigma f. I just divided both sides by sigma f. My mass is then equal to 0.733, and I'll use my ellipses trick, divided by my net force, which is 7.05 times 10 to the 4, and I find that my mass, I believe, is 70,456.666, or to 3 sig figs, 770,500 kilograms. So using the things that we previously know or have previously learned about to find details about things in kinematics or in dynamics problems is definitely a thing that we're going to experience. Third type of example. A 3,000 kilogram car is broken down, it's probably my Volvo, and being towed. If the tow truck pulls forward with a 9,000 Newton force and the car experiences an 8,000, that's supposed to be an 8,500, I've got an extra 0 in there. 8,500 Newton frictional force backward, what is the acceleration of the car? So notice how this is the first one we've come across that has more than one force. It doesn't give us a net force. We're going to have to find out what that net force is. So whenever we're given more than one force, or if we're ever stuck in a dynamics problem, we're going to want to draw a picture. We're going to talk more explicitly about how to draw good pictures tomorrow, but for today, I'm just going to draw my car as a box, and I want to put my forces on my box. I'm going to have an applied force, which is 9,000 newtons going to the right, and I'm going to have an 8,500 Newton force going to the left, and that's my diagram for this picture. It doesn't need to be complicated, simpler is better. We really only want to show the object and the forces on it. So what you'll notice is my forces are in 2 different directions. So we're going to have to come up with some type of sign convention. What you're going to want to do is choose the direction you accelerate to be positive. If you can't figure out off the top of your head which direction that is, usually that'll be okay. Just choose a direction randomly, either left or right, or up and down. But now I have a pretty good idea that if 9,000 newtons are pulling to the right and 8,500 newtons are pulling to the left, that my positive direction will in fact be to the right. This is important because when I look at my Newton's second law, sigma F is equal to ma, what this means is my applied force is 9,000 newtons, and my frictional force is going to be negative 8,500. So what that means is when I'm looking at forces, I like to work on the left-hand side of my equation first. My FA will be positive. but my force of friction is going in the opposite direction, so it's negative. So this is where we get our directions from, and they should come in this line of algebra, and then you shouldn't have to put in another negative sign. Do not put the negative sign in twice. So I'm going to get rid of this negative 8,500, and I'm actually just going to leave my diagram like that. My force applied is going to be positive. My force of friction is definitely going to be negative. And I'm looking for the acceleration. So I can do my little bit of algebra. I can divide both sides by mass. Acceleration is equal to FA minus FF divided by m. Notice how this is the only equation that I actually gave you. This is the only equation that may or may not be on a formula sheet. The next line of algebra could be drastically different for any question. So you can't memorize anything here. You actually have to understand how the Newton's second law works and practice applying it. So practice going through those logical steps. Draw your diagram, put your forces on, come up with a sign convention, and then substitute appropriate forces into Newton's second law. I can throw some numbers in. I've got a 9,000 minus 8,500 divided by 3,000. And my acceleration is then equal to 0.1666666. I write those out in case there's a second step to a question and I want to know it again, but to 3 sig figs, it's a 0.167 meters per second squared.
Thank you for watching, and I just wanted to remind you guys a couple of keys for success. Number one, you got to do the practice questions. If the things I'm saying make sense, that's phenomenal, but you still have to practice and make some mistakes on your own. And that goes along with number two. If you get stuck, ask me questions, get in touch, write me an email, make an appointment, or leave a comment on the YouTube video. And step number three to success is look after yourself. Eat good food, get some exercise every day, and socialize as much as you can right now. I hope you guys are all doing well, and I will talk to you soon.